All right, so the purpose of this video is to give us an introduction to well, four types of n-by-n matrices. What we're about to go through here is really not meant to be deep. It's just merely meant to be four definitions of four different types of matrices that have a particular structure, just to introduce you to these notions, because as we get later in the course, what is an upper triangular matrix, a lower triangular matrix, a diagonal matrix, or a symmetric matrix is something that, well, having previous knowledge through an experience like watching this video will be useful, because there's sort of these four types of matrices supply a nice collection of examples for us to access. So first thing to note is that we're talking about n by n matrices here. So rather than n by m matrices, which might be non-square, here, when we're talking about n by n matrices, we're talking specifically about square matrices. So 2 by 2, 3 by 3, 4 by 4, 5 by 5, something like that. Also, as I've defined the matrices here, and we'll discuss the definitions and how that ultimately sort of leads to, in some sense, the naming of them and what they ultimately look like, let's just recall that whenever we use subscripts ij for any given matrix, we're referring to the element, the particular entry, that is in row I, column j. Remember, we always list the row before the column. So when we say aij, we mean row I, column j of our matrix A. So let's get started then. So with the upper triangular matrices, we say a matrix is upper triangular if the entries could be anything when I is less than or equal to j and are 0 otherwise. Okay, now to sort of make sense of this, let's think about this for a second, because here, when the row number is less than or equal to the column number, we could be anything. But whenever we're in another case, we've got 0. But what is this other case? Well, when you talk about the row number and the column number, if you're comparing them, they're either less than, greater than, or equal to. So if less than or equal to is covered above, then the otherwise case here, note, is when I is greater than j. And in fact, let's focus on that, because here we're saying that the row number is greater than the column number. So to give us a visualization of what such a matrix would look like, let's consider like maybe a 4 by 4 example. Remember, we've got to have a square matrix here, so let's consider something with 4 rows and 4 columns. Now, when is the row number greater than the column number? Well, in row 1, note never in row 1 is the row greater than the column, because the column is always at least 1, and since the column is always at least 1, the row number 1 is never greater. What about row 2? In row 2, you can have the row number greater than the column number in the first entry. All other entries in row 2 have the column number that's at least as big as the row number, but the row number is bigger than the column number in row 2, column 1. And based on the definition of an upper triangular matrix, that means that that entry has to be a 0. What about row 3? In row 3, you could have a couple positions where the row number is bigger than the column number, and that would be row 3, column 1, and row 3, column 2. Once you get out to row 3, column 3, you no longer have the row number bigger, but when you're in the first 2 entries of row 3, the row number is bigger. What about in row 4? Well, the first 3 entries of row 4 would have the row number being bigger, and that would force those entries to be 0. Because again, to be an upper triangular matrix, the entry is forced to be 0 when the row number is bigger than the column number, and otherwise the entry could be anything. So that means we've now accounted for all of the positions that are forced to be 0, and the rest could be anything. So here is the basic structure of an upper triangular matrix, an upper triangular 4x4 matrix to be specific. And when you look at this, you can kind of see visually why we might even refer to this as an upper triangular matrix, because when you look at the entries that are non-zero, they sort of all exist within the upper triangle of the matrix, or at least an upper triangle, namely among all of the positions at the diagonal and above. Okay, so here's an example of, here's a general picture of what a 4x4 upper triangular matrix looks like. And of course, this could be generalized in some sense to 5x5 or 6x6, but the idea would remain the same in the sense that the entries below the diagonal would be zeros by virtue of the fact that their row number is greater than their column number. The entries above the diagonal and on the diagonal could be anything. Okay, what about a lower triangular matrix? A lower triangular matrix could have any value when the row number is greater than or equal to the column number, but must be zero otherwise. Well, this actually feels very similar to what we were doing in the last example, because what is the otherwise? Well, if we could be anything when the row is greater or equal to the column, then the otherwise is when the row is less than the column. So where are you in the matrix when the row is less than the column? Because when the row is less than the column, the matrix entry is forced to be zero. Well, let's look at an example. Again, we'll just go 4x4 for the sake of seeing something in some amount of generality without having to draw something that's too large or cumbersome. But okay, here's the question. When is the row number less than the column number? Well, in row 1, you are not less than the column number in column 1, but the row number is less than the column number in column 2. The row number in row 1 is less than the column number in column 3, and row 1 is also less than column 4 numerically. So each of those entries are forced to be zero because based on the definition of a lower triangular matrix, the entries of the matrix have to be zero when the row number is less than the column number. What about in row 2? Well, in row 2, these entries would have row number less than column number when you would get out to column 3 or column 4. Because, of course, 3 and 4 are greater than 2. What about which column numbers are greater than 3? Well, only column 4. And in fact, then, when you get out to column 4, you are not forcing any of the values to be zero, because in column 4, you can't have the row bigger than the number of columns, because we've got a square matrix. There's only 4 columns, and, well, by the 4th column, you're not bigger in column number than row number. So long story short, in each of the rows, we've now established where the zeros are forced to be. And based on the definition of lower triangular, everywhere else, you could be anything. So filling in those asterisks accordingly to imagine where those anything values could be, we've got a matrix of this kind. You've got zeros above the diagonal, and your non-zero entries are located at the diagonal and below, forming a lower triangle. Now here's the thing to think about just for a moment. Anywhere where there are asterisks, there could be anything. So you could have a zero in one of those positions. Hell, you could have a zero in all of those positions. But when you talk about a lower triangular matrix, the values where the asterisks are could be anything. So they don't have to be zero. The only positions where you're forced to be zero are, well, in the case of a lower triangular matrix, the values that are in the upper triangle above the diagonal, and in the upper triangular matrix where you're forced to be zero is only in the values below the diagonal. So you're forced to be zero in those cases. Everywhere else you could be anything. You could be zero, you could be something other than zero. You could just label these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you would have 10 numbers among the possible values. Okay, so we've got the upper triangular matrix, we've got the lower triangular matrix, and what it sort of looks like. Again, these are just 4x4 examples. but you could trim this to a 3 by 3. You could also augment this to a 5 by 5, and the same idea would manifest. All right, so what about a diagonal matrix? A diagonal matrix, the entries could be anything when I equals j and are 0 otherwise. Now, otherwise here, if I equals j is anything, then we're forced to be 0 when I is not j. In other words, when I is greater than j or I is less than j. So now let's think about this one, because this will be interesting to look at as well. And actually, when you think about when I equals j, there's only so many positions where that's the case. Let's just throw in these asterisks straight from the go. Because when I is not equal to j, that's a ton of values within our matrix. But the values where row number equals column number, those are very particular. So when you're in row 1, the row number equals the column number only in column 1. Here we could be anything. Everywhere else, zeros. In row 2, column 2, we could be anything. Everywhere else, zeros. Row 3 would correspond to column 3 where you could be anything, but everywhere else zeros. And continuing that trend down to column 4, you now see a picture of a 4 by 4 diagonal matrix. And in fact, the name diagonal matrix you can see indicated in the fact that where your non-zero values could be are along the diagonal of the matrix. The identity matrix would be an example of a diagonal matrix. And for that matter, so would the zero matrix, because the zero matrix would just happen to have zeros where those asterisks are. Just a note, the zero matrix is also lower triangular and upper triangular. And for that matter, the identity matrix is also lower triangular and upper triangular. Because the identity matrix, you would be allowed to have ones along the diagonal, and you'd be allowed to have zeros below the diagonal. Similar story for the upper triangular. Okay, so we've got a picture of what a general upper triangular, lower triangular, and diagonal matrix looks like. Let's take a gander at symmetric matrices. You look at the definition of these matrices, these symmetric matrices, and it looks a little different from the previous cases, and in fact symmetric matrices are a bit different. So here what we're saying is Aij equals Aji. The entry in row I, column j, has to be equal to the entry in row j, column I. That's kind of interesting. And to take a look at the symmetric matrix, rather than just fill in asterisks, I'm going to fill in actual numbers so that we can see what's going on here. And yet again, I'm going to use a 4 by 4 as an example. So we've got row 1, row 2, row 3, row 4, and just as well column 1, column 2, column 3, column 4. Okay, now Aij has to equal Aji. Let me fill in, I'm just going to fill in the values for this matrix like sequentially, and I'll just start with 1. Why not, right? Okay, so I'll start with 1 in the 1, 1 entry. Now, based on the definition of symmetric matrix, what is in the 1, 1 entry has to be equal to what's in the 1, 1 entry. Well, that's true trivially. That's, A1, 1 has to be A1, 1. Okay, so that entry is 1, fine. Okay, what about A1, 2? I'm going to fill a 2 in for this one. And now, what do we know about this entry? The entry that's in A1, 2 has to be equal to the entry that's in A2, 1. So the entry that's in row 1, column 2, also has to be in row 2, column 1. So by virtue of the symmetric definition, the 2 which has been inserted into row 1, column 2 has to also be in row 2, column 1. Similar story now for row 1, column 3. Row 1, column 3, let me put a 3 there just to give a different number so that we can sort of feel this out. Row 3, column 1 has to be the same in, row 1, column 3 has to be the same in row 3, column 1. Continuing along, row 1, column 4, let me put a 4 there. That has to be the same value as is in row 4, column 1. Next, sort of moving along here, we sort of have been going along left to right, top to bottom like we read in English. Let's keep moving along the matrix as such. We know that we've got a 2 forced to be in the position row 2, column 1, since that 2 was in row 1, column 2. Let's take a look now at the next position. This would be the 2, 2 position. This could be anything because, well, heck, A2, 2 is always equal to A2, 2. So this 5 is just this 5. It doesn't have to be repeated anywhere else in the matrix. But when we go to row 2, entry 3, put a 6 there, what's in position 3 of row 2 has to be in row 3, position 2. So row 2, column 3, and row 3, column 2 have to be equal. Similar story for row 2, column 4. Let me put a 7 there. That 7 has to be replicated in row 4, column 2. So now, again, moving top to bottom, left to right, or left to right, top to bottom, we are now at row 3, position 3. That could be anything. And in fact, whatever that anything is not forced to be anywhere else, because A33 equals A33 by virtue of the, symmetric property of equality. Okay, now next, what about row 3, column 4? That could be anything, but whatever is in row 3, column 4 has to also be in row 4, column 3, forcing that 9 to be below as well, leaving a final possibility in the last position. Okay, so we've filled in a general picture of what a symmetric matrix looks like, sort of using numbers to see it through. And then you wonder, why would we call this a symmetric matrix? Well, if you imagine the diagonal being like a mirror, the symmetric matrix is actually, well, symmetric about that mirror. So position, the element that's in the position 2, 1 is symmetric about the diagonal. So too, that number 3 that we inserted, and so too the 6, so too the 4, so too the 7, and so on. So what you can see is the symmetry that exists in terms of why we call it a symmetric matrix is in some sense a visual symmetry whenever you put in that diagonal as a dashed line of symmetry. But long story short, nothing to beat ourselves up here over in terms of what these matrices are. We just want to familiarize ourselves with what we mean by this. Upper triangular matrix, square matrix, where all of the non-zero entries are in the upper triangle, diagonal and above. Lower triangular matrix, that's a square matrix where all the non-zero values are in the lower triangle, namely the diagonal and below. Diagonal matrix, all the non-zero entries are located along the diagonal, and symmetric matrix are matrices where the entries are symmetric about the diagonal line.